All right, welcome to the overview of the procedure sections of the second week of Lab 1. This week, we'll focus on using the Afterglow image analysis system. And this is just intended to be a brief summary. Within each procedure section, you'll find a video tutorial that describes how to do the task in much more detail. This will just be a quick summary of each of these sections and each of these tasks. So let's slide on down to week 2. And we'll open up the first section, which is planet and dwarf planet images. And the first link we come across is Afterglow. I'll open it up here. So this is Skynet's image analysis system. If you're logged out or have never logged in before, you'll log in using your Skynet credentials. You can see I have a number of images already loaded from work I was doing before. Now in this first tutorial, you'll learn how to adjust the brightness and contrast levels in images to bring details out in them. In particular, in this first task, you'll take the images of the planets that you observed from last week, and also the dwarf planet series, which is partway between Mars and Jupiter in the asteroid belt. You'll zoom into these worlds all the way in, have them fill the screen, and you'll adjust the brightness and contrast levels to bring out as much detail as possible. Some of these worlds are quite large in an angular sense, and you'll be able to see a good deal of detail in them, such as Jupiter, Saturn. You'll be able to make out the phase of Venus. Some of the worlds are quite small or quite far away, and you won't see much detail at all. Now, to set your expectations, here's an intermediate case. This is a picture I took of Mars a number of years ago when it was about as close to Earth as it gets, which means it's going to be angularly large, and so we can see some detail. Now, the picture on the right is what Mars actually looked like at that moment in time if you were viewing from space or from in orbit around Mars. Now, you've seen lots of pictures of planets, crisp, beautiful pictures, and most of those were taken either with the Hubble Space Telescope or by spacecraft in orbit around those worlds. We don't have that luxury. You're going to be observing with a small telescope on the surface of the Earth, looking through Earth's atmosphere all this distance away. So your images will come out something like what I have here on the left. Just to set your expectations, you're not using a space telescope, and we're not going to these other planets. But still, you can see some detail. Like here, I can see the ice cap, the polar ice cap of Mars, matching up over here. In fact, the dark regions match with the dark regions, the light regions match with the light regions. And again, you'll see more detail in some worlds and less detail in others. Once you've finalized each of your images, you'll save it as a JPEG file and upload it here. And in this box, you're going to describe the detail you see in your images. Even for the worlds where you don't see much detail, you can still comment on how large the world appears compared to the background stars and surrounding moons. Okay, let's go to the next section. In this section, you're going to learn how to measure the angular diameters of objects. There are 2 tutorials. In the first tutorial, you'll learn how to determine which telescope took your picture and when it took your picture. In the second tutorial, you'll learn how to use Afterglow to measure the angular diameter of the world in your image. Then for each image from the section above, all the planets and the dwarf planet series, you're going to zoom in, adjust the brightness and contrast levels so you can see the edges as well as you possibly can, and then you're going to measure the angular diameter of that world to the nearest 0.1 arc seconds and enter that in the table down below. And just a couple quick notes. In the case of Saturn, we're not going to measure the size of the world, but the angular diameter of its rings. But for all the other worlds, just the diameter of the world. Also, Some planets may appear to be in a phase, Venus in particular. In that case, you're going to measure the angular diameter from tip to tip, the long distance, not the short distance across, but the long distance from tip to tip. Then you come down to this table. In the first column, you'll indicate whether the object was observable. When you're doing the lab, not all objects will be. Indicate which telescope took your image, the date and time, the universal date and time, month, day, year, hour, minute, second, entered in this format, that your image was taken, and the angular diameter that you measured in arc seconds. Finally, you'll need to enter your name into this box to attest to the fact that you collected this data yourself. It's like an honor code pledge. Okay, let's move on to the next section. In this section, you're going to use a program called Stellarium to check your answers from the previous section. You can get a copy of Stellarium here. This is free, downloadable planetarium software for your computer. We use it not only in the first lab, but in a number of the upcoming labs as well. As you can see, it works on a variety of operating systems. Once you download it and install it, you should run it. If there are any technical problems, then come back to this page and instead install one version back. That normally solves whatever problems may arise. Now, in this tutorial, we'll show you the basics on how to use Stellarium. Basically, how to simulate the sky as it looked when Skynet took your picture. Then you can compare the information you get from your picture to the information that you can read out of Stellarium. After the tutorial, we have a few reminders. I'll let you read those after you watch the tutorial. And then for each image from the previous sections, you're going to enter the observation date and time that Skynet took that image into Stellarium, zoom into that particular world, and read out its true angular diameter to the nearest 0.1 arc seconds, and then enter that in the table below. Again, for Saturn, you're going to want to read out the angular diameter of its rings. But for all the other worlds, just the angular diameter of the world. Then for each of these, for which you were able to collect data, you'll calculate the percent error using this equation here, using the measured value, which is in the table in the previous section, the true value, which is in the table in this section. You take the difference, you take the absolute or positive value of that difference, divide by the true value, multiply by 100%. That's your percent error. That goes here. Again, you'll have to sign your name. It's another honor code pledge. In this box, you'll enter a sample calculation showing how you calculated percent error for just one of your calculations. And then here is your first discussion of sources of error. You'll see these in every lab. Students sometimes have problems with this, so this is something you'll want to focus on and come back after the fact, look at the answer key to get an idea of what a good sources of error discussion involves. Now for this one, I want you to think about atmospheric blurring. The atmosphere blurs incoming light by about 1 arc second. So for a large world like Jupiter or Saturn, which may be 30, 40, 50, 60 arc seconds across, an additional arc second of blurring is not a big deal and should result in a small percent error. But for a small world like Ceres or faraway worlds, which may appear small in an angular sense, then we'll take Ceres for example. Its angular extent, its true angular extent, is less than an arc second. So if you then have an arc second of blurring on top of that, that will lead to a very large percent error. Anyway, I want you to think about this effect and how the effect differs for objects of different angular sizes when writing this discussion section. Now, when discussing sources of error, try to avoid the phrases human error, measurement error, calculation error. Those do not count as sources of error because these are all fixable. If you made a calculation error, you should recalculate before submitting it. If you can't figure out why you're having the errors that you're having, then you should talk to your instructor and they can advise you. All right. In this section, we're going to switch over to that second set of images that you took of the gas giants using filters that let more light through, making it easier to detect the faint moons in orbit around them. In this section, you'll use afterglow and stellarium in concert to identify these moons in your images. Using afterglow, you'll adjust the brightness and contrast levels to bring out as many moons as possible. And you'll use stellarium by entering the date and time that Skynet took your image to simulate the sky and to simulate this world and to simulate its moons as they appeared at that time. You'll then compare the two images to identify your moons. Now, this tutorial will show you how to do all that. It will also show you how to mark and label the moons in your images. After you watch the tutorial, there are a number of reminders, and I'll let you read those separately once you've watched the tutorial. There are a couple of notes here. First of all, if you don't see any moons in your image, there may have been a thin layer of clouds when Skynet took your picture, in which case you'll probably need to go back and retake that picture. Also, students sometimes have trouble finding Neptune's moon, Triton. It's a large moon. It's the only moon you can see around Neptune with these telescopes, and it will be the point of light right next to the planet, very close in. Then for each of the planetary systems that you could observe, you're going to zoom in, mark and label the moons, and save your image as a JPEG file. You'll then upload these JPEGs here into WebAssign, and in this last box, you will enter one fact about each of these moons. You can Google these moons, learn a little bit about them, and enter one fact about them in this box. Okay. In this next section, we're going to switch over to the images you took of the dwarf planets, Pluto, Haumea, and Makemake. Now, many of these worlds are very small and very far away, and they don't appear any brighter or any different than the background stars around them. So in this tutorial, you'll learn how to compare your image to an archival image, an image that was taken decades ago, to identify which point of light in your image is the dwarf planet. The tutorial will show you how to line them up, and you'll mark similar stars in both images, and then you'll look for the point of light that's in your image that's not in the archival image. And this is because the dwarf planet moves, it's orbiting the sun, and it is in your image right now, but it was not in this part of the sky decades ago when the archival image was taken. You'll then mark and label the dwarf planet in your image, and you'll save these, and you'll upload both your image and the comparison archival image into WebAssign here. Then, for each object that you were able to observe, Google it and enter one fact about that object in this box. And that brings us to our final section, which is pretty straightforward. And these are the deep sky images that you took, and also the image that you took of Earth's moon. You'll load these up in Afterglow. You'll adjust the brightness and contrast to bring out as much detail and as much structure as possible. You'll then save them as JPEG files, upload them here, and again, Google a fact about each one and enter it in the box here. All right, that brings us to the end of this overview video.